So there is a test for whether or not something is a function. Do you remember what it is? A simple geometrical test. If you have the graph of something, which of those is a function?
The first one. Yeah.
Okay, this one?
No.
No. This one?
No.
No. Okay, why not? How can you tell just looking at the picture that those are not functions?
When you draw a vertical line, it has to only intersect once.
Yes, exactly. We fail right here. Because for this value of x, our function machine is supposed to spit out one value, and it would be forced to spit out two, making it a non-function. Same thing here. This value of x, we have two potential function values, which break our machine, and we don't have a function anymore. Okay, so given that, we now have kind of a new class of functions, which is ones that pass the horizontal line test. Okay, so that is just, here's one that passes, and here's one that fails. Pass, fail. So you can see the idea. We have two intersections. Oh, this does not pass. I lied. Try again. We'll go with that. That passes. Because here I have multiple points of intersection. Here I just have a single one. Alright, why do we care? Well, the reason why is because for these functions that fail the horizontal line test, if we were to switch around their x and y values, so just kind of tilt your head and then look at it this way and say, is it a function? They would now fail the vertical line test. The answer would be no, they're not a function. So a function that passes the horizontal line test has what's called an inverse.
It's like a super powerful function.
Exactly. Okay, so you guys were asking last week about what you do in grad school. Like, what I studied in grad school was something called ring theory. And rings are sets that have certain characteristics. And you guys work with rings all the time, you just don't realize it. Like, the real numbers are a perfectly valid ring. And in order for something to be a ring, it has to maintain what's called closure under multiplication and division. You define the operations that it's closed under, but the real numbers are a ring that are closed under multiplication, division, addition, and subtraction, which means that anytime I add two numbers, I get another real number. If I divide two numbers, I get another real number. If I multiply two numbers, I get another real number, and so on. The integers are not closed, say, under division, because if I divide two real numbers, or two integers, I don't always get a new integer. I could get a fraction. So they're different than a ring. This is a total aside here. But anyway, inverses are things that exist inside of rings, right? Every real number has an inverse. It's 3 and 1/3, all right, inverse numbers. What happens when I multiply a number by its inverse?
You get 1.
You get 1. 1 is the identity, which is another characteristic that these rings have. Well, it turns out that functions can be their own kind of ring, and because we now have this idea of inverse functions. And in generally speaking, rings have to be closed under multiplication, and when you multiply an element of your ring by its inverse, you should get the identity, which in numbers is 1. In functions, the identity function, do you know what that is?
It's y equals x.
Y equals x, exactly. So what's going to happen here, when we multiply, and the operation is not actually multiplication in the ring of functions, it's composition. When we compose a function with its inverse, because it has the property of being a ring, we get the identity function. So inverses have, just like everything we've looked at so far, we've looked at them both algebraically and geometrically. So this is a geometric way of identifying whether or not a function has an inverse. It will have an inverse if basically you could switch the x and y axes and still pass the vertical line test. So we have the horizontal line test for that. Now, we denote the inverse. F is the function f to the minus 1. Now, in real numbers, when you put a minus 1, it means 1 over. And when you multiply a number times 1 over that number, you get 1, which is the identity. We're going to use this notation now to mean the thing that when we compose it with, we get back to the identity. So, algebraically, we know that f of f inverse of x has to be equal to x, and f inverse of f of x also has to be equal to x. So in some sense, inverse functions kind of undo each other. And
Because
along
f
this,
over f is 1.
not f over f.
I mean, f
The-
1 over f times f. Wait, yeah.
is
wait.
1, which is not x. So that's different.
No, but 1 times x is x.
Well, that's obviously true, yeah. But no, I don't want you to confuse multiplication with composition.
Okay.
We're dealing with something that they're non-numbers, so the operation that we deal with now. We can multiply functions, but it turns out that that's not the most important operation when you're dealing with functions. This function composition is more important. And so basically what happens is that, let's say that the point AB is on the graph of f. So in other words, f of A has to equal B. Okay. The inverse is going to kind of undo this. So to undo this, that would mean that f inverse of B would have to be what?
B comma A?
Close.
A?
This is just going to be a single value. Right. So f inverse undoes whatever A did. Or whatever f did. F took A and mapped it to B. So f inverse is going to take B and map it back to A. And that tells us that the graph of B comma A is on the graph of f inverse. So what's happening with these inverse functions is that the domain of one is going to be the range of the other, and vice versa. They flip-flop the roles of the x and y axes, which is why you need that horizontal line test to work, because you're just changing the roles of the x's and y's, which means your domains and ranges are switching around. Okay, so I'm gonna just let you guys now start off slowly. Oh, this isn't what I want to do. Never mind.